Welcome to Forecast Forward. Today's session is choosing the right AI model for your business. And so, last week, this is the second of a series. We have five of these. Last week, Mastering Time Series Forecasting, we laid the groundwork for understanding AI powered forecasting, specifically looking at how time series data can throw traditional AI models for a loop because of its unique temporal dependencies. So we talked about using internal and external data sets to drive predictions and some innovative capabilities like time to vec that help you do this when data is limited. So if you couldn't join us last week, the webinar is available on demand on the Ikigai website. And if you're joining us for the first time today, you haven't missed anything. We'll keep building on the fundamentals as we go into these practical applications. So let's move into introductions. I'm really excited to introduce our panelists today. The first is Vinayak Ramesh, and he is our co-founder and chief customer officer at Ikigai. So he is a serial entrepreneur recognized in Forbes 30 Under 30. He has a bachelor's and a master's in engineering and computer science from MIT. And then also we will have Camil Blanchet with 3 years on our applied AI and solutions team. He specializes in advanced forecasting solutions with a background in neuroscience and AI. So he's constantly applying our technology to a wide variety of use cases and has a really deep understanding of what people are seeing out there in the real world. So with those introductions out of the way, I'm going to pass it off to Vinayak. Thanks, Vinayak, for taking the time today.
Awesome. Hi, everyone. Great to meet you, and thanks for joining. So today we're going to be talking about different types of time series models and how to pick the best one for you and your use case. When it comes to AI, there's a lot going on and, lots of information out there. Do you use, especially when it comes to time series, do you use LLMs? Do you use deep learning? What other models are out there for time series forecasting? And in particular, when do you use a certain model? So, we typically see a few types of models when it comes to time series, and there's also different capabilities that we want our models to do. When it comes to time series, the baseline is prediction or forecasting. That's typically the first thing that everyone starts with. Now, on top of that, you might want to do things like planning, what if analysis. But in general, these are all very, very numerical use cases. We hear a lot of questions about whether LLMs are suited for this, and one of the things where we kind of draw the line is LLMs are really, really great when it comes to data, unstructured data like text or even dealing with images. But for numerical tabular data, especially with time series with complex historical patterns, we typically want different types of tools. Now, there are interesting things about LLMs and foundation models that can be applied to time series, which I'll talk a little bit about in a second. So when we think about the different models when it comes to time series, there are usually 4 different types. There's the traditional statistical models like ARIMA. We have deep learning models like LSTMs, foundation models, which we spoke about, which could be LLMs, or more recently, there's been time series specific foundation models. And then we have graphical models, which you may be less familiar with, but this is the approach we're pioneering at Ikigai, and looking forward to telling you a lot more. So statistical models were really popularized by ARIMA, which came out in the 70s. So ARIMA stands for Autoregressive Integrated Moving Average. Before ARIMA, we were using a lot of simpler approaches like exponential smoothing or moving averages. These are great when you look at very recent data, but they couldn't handle the complex patterns we often see in real world data. Things like, trends, seasonalities, looking at, a longer time window to look for correlated patterns. And, ARIMA was really one of the first models that combined some powerful ideas to allow us to better forecast time series models. So one of the most important parts is, I mentioned ARIMA stands for Autoregressive Integrated Moving Average. So the autoregressive part, which really looks at correlations between past values across all of your data to predict what's coming next. Before that, we were only looking locally at a few values. And then it incorporates the integration, which allows us to take into things like removing the effects of trends, forecasting trends separately. There's different variations of ARIMA that allow us to incorporate seasonality. And of course, we have moving average, which allows us to take into account more short-term patterns as well. So when you think about a lot of the models that are coming out of your business systems, most likely they're using a version of ARIMA or a version of statistical forecasting. So the second bucket is really deep learning or neural networks. So again, neural networks have been around since the 80s, but in the 2010s is when they really got very, very popular because of all the compute that was available that allowed us to deal with much larger and larger data sets. Now, in terms of time series data, the real breakthrough for using neural nets for time series data came out with what are called LSTMs in the late 90s. So LSTMs really stand for long short-term memory. So, earlier models, like I mentioned, similar to before ARIMA, we could take into account, few local data, but the LSTM allowed us to find correlations across, longer time horizons in your data. So, for example, if, data from, 2019 looks a lot like patterns today, we could actually learn that there's a correlation rather than just using, the last few weeks or last few months of history. And again, in the 2010s, with more computing power, neural networks, especially LSTM, started being applied to larger and larger time series data. And they really got, initially popular with things like, speech use cases, speech recognition, and so on. So now, the hot topic is really foundation models and LLMs. Are these the right approach? They're really, really effective at, doing things like content generation, creating images. Can they be utilized for time series? So, regular LLMs, you think of ChatGPT, were primarily trained on the whole internet's text data. And what's interesting is while it was primarily used for text, there's similar ideas that could work for time series data too, which is why people have been exploring this. So LLMs or large language models are based on what's called the transformer architecture, which is really effective at modeling sequences. So when you're typing into ChatGPT, it's basically taking your query and looking for some sequence of words that it's seen in its history and then effectively doing pattern recognition. So it makes sense that this might actually be effective at not just sequences of words, but sequences of numbers. And kind of more recently, within the last year or two, researchers have started creating foundation models specifically for time series. So models like ChatGPT, rather than being trained on the world's text data and websites, models that are pre-trained on massive amounts of diverse time series data that might be available in the public domain. So, census data, weather data, learning all sorts of patterns that might match a specific problem. So again, foundation models, whether it's LLMs or time series or like pattern recognition powerhouses. So instead of starting from from scratch, these come preloaded with effectively knowledge about how different types of time series behave. And they're looking for, if you're a particular time series, the same way in ChatGPT, we're looking for a sequence of words that it's seen before that's matching on the internet, that's matching what you typed in. We're looking for some time series that's in its preloaded set of data that matches most similarly what you've provided it to try and forecast. And in a second, I'm going to walk through kind of the pros and cons of each one. So finally, we have graphical models. Graphical models, in one form or the other, have been around since the early 1900s, been used in everything from statistical physics to biology to GPS to speech recognition, machine vision. They're really, really good when working with sparse tabular data, and applying them to time series data is kind of the novel approach that we're taking at Ikigai. So, traditionally with graphical models or large graphical models, the reason they haven't been used for a lot of enterprise use cases, especially in time series, is for a couple of reasons. One is they required domain experts to come in and tune the model for the particular problem at hand. But in an enterprise, you don't have the time to have someone come in and tune a model just for your particular ERP, and then the next customer's ERP, and then you want to bring in other data sets for your particular domain. That's not really feasible. And second was, how do you kind of run this at scale across large data sets? So, at Ikigai, or related to Ikigai, there's been a couple of breakthroughs. The first one was from, our co-founder, Devarvit, and his colleagues around domain agnostic model learning. So the way I think about this is, if your data is one large spreadsheet, you want to learn all the correlations across the different cells in your data. But like I said, before this, an expert had to come in and help specify how all of that would work. But with domain agnostic model learning, you can think of it as, you give your spreadsheet, it doesn't even matter what the column headers are or what the domain is, you can automatically learn the best model and all the correlations across all the cells in your spreadsheet. Now, the second problem was, okay, that's great, but now how do we do this at scale in an enterprise for enterprise data? So that's really where our PubSub innovation came through, which by myself and Devarvit, which basically enables doing this sort of learning at scale in parallel across large data sets. And that's what effectively enables us to train these large graphical models on demand on an enterprise's data. And on top of that, there's the Ikigai platform, which allows you to actually do the forecasting and build AI applications on top of our LGMs, which we'll go into details a little bit later in this session. So I've gone through these different models, but now the key question is really like, how do you pick which model is the best for different use cases? Obviously, each is going to have its own pros and cons. And the Harvey balls and the categories are initial way of explaining it. I'm going to walk through kind of how we think about it, and if we want to dive into details, it's hard to put all in one slide, but we can kind of walk through specific questions in the Q&A section. So the way we kind of think about it is, when you're trying to pick the best model, the first thing is looking at your data. And I really think of two dimensions. One is, what's the size of your data? And the second is, what's the complexity of your data? And I'll walk through what each of those really means in a second. So the first question is, when you're evaluating models, is how much data do you have? On one end of the spectrum, if you're doing something like demand forecasting, in many cases, you actually have very sparse data. So say you're taking daily sales, you're a retailer and you're taking daily sales for a SKU for the past 2 years, and you're trying to build a model that forecasts SKU sales out for the next few months. So for that particular SKU, if you're taking daily sales for 2 years, that's less than 1,000 data points. That's really, really small. That's not a lot of history. On the other end of the spectrum, if you're working on speech or audio data, where you're collecting data that varies every second, you're likely to have millions of data points. That's orders of magnitudes bigger. So, first is really deciding where on that spectrum you fit. The second dimension is really the complexity of your data. The simplest is when you only have one time series, like a single SKU, which is what we refer to as a univariate time series. But in many cases, in the real world, like as you're this retailer, you're forecasting for multiple SKUs. So you have multivariate time series. In addition, there are likely other structures in your data, such as hierarchies. So for example, going back to the SKU, let's say the SKU represents a red shirt. Now, your red shirt might belong to the category of clothing. Maybe you have a different category with shoes, a different category with jackets. Now, you might want to forecast how much of that red shirt is also sold in a particular store, and that store belongs to a state, and that store belongs to a region. So those are actually examples of two different hierarchies that are present in your data. There's the product hierarchy, and then there's a geographic or regional hierarchy in the data. And you might even have, in time series, you also have time hierarchies. You want to forecast at the daily level, weekly level, monthly level, and all of those should basically reconcile with each other. So in most business applications, you actually have very limited or sparse data, but highly complex data. It's typically multivariate and contains several hierarchies. Now, statistical models like ARIMA can work really well in this realm of limited data, but they're not necessarily able to capture all of the complexity, such as multivariate or hierarchy, without a lot of fine tuning and a lot of work. They're great for univariate time series and work very well out of the box for non-hierarchical data. Now, neural networks on the other end of the spectrum, they can capture the complex relationships in these data, like long-term relationships, across hierarchies, across different time series, such as different skews, but they're very data hungry. They require a large amount of data to work with, to work well, like millions or billions of data points. And that's what's made them great for time series use cases, such as audio or speech recognition, which is where they originally came out from. Now, LLMs and foundation models, interesting, they require tons of data to even get started, because remember, they're trained on the internet's whole data. So while they require large amounts of data to get started and can recognize these patterns in the data set that they have, they're not necessarily able to handle the complexity of multivariate and hierarchical data found in business applications. Now, furthermore, they need to have seen a business that looks identical to yours in the training data, which is difficult because they're primarily trained on public data, and your business data is going to be proprietary. Second is, you most likely won't want your proprietary business data being fed in the model to help forecast for other businesses. So this is obviously foundation models for whether it's using LLMs or time series is very new, so it's an active area of research. But LLMs tend to struggle quite a bit when it comes to even working with numerical data, and they become very, very expensive to train with large amounts of data. And then the time series ones work as well as your large training set of, if you're able to train on the internet's whole data, then that's great, and your business data has to be represented within that public data. And of course, it can have a level of complexity that we typically see in a lot of business use cases, such as hierarchies or multivariate time series. Now, coming to graphical models, they really succeed at two things. They're great at working with sparse data, and they effectively capture relationships across your data. So this makes them ideal for many business forecasting applications, as they're working as typically like I mentioned, you have sparse data that's tabular and data that's highly complex, that's multivariate and hierarchical. So for a lot of these business forecasting use cases, graphical models really hit that sweet spot because they're able to tackle this sparse data along with that complexity. And in addition, they're trained bespoke on your data, so it captures the relationships in your data rather than having to be trained on the internet's whole data. So this is great. So we've kind of walked through what some of the different models are and in which scenarios you might want to choose the best model for your data. But how do you actually carry this out in reality on your actual data using your actual business systems? So that's really where the Ikigai platform comes in. So, there's over 200 data connectors that bring in data from all of your different enterprise data sources. This can then get fed into the product, in particular, into our platform, in particular using our AI Cast product, which automatically picks the best model for your data. What we see is that in many use cases, because in the real world, you might have thousands or tens of thousands or hundreds of thousands of different time series, your data might actually require different models for different time series in order to get the best prediction. So maybe, North America is a fairly new region, so you don't have much data, so it requires a different model versus, maybe you've been selling in, your business is Asia-based and you have tons and tons of data in Asia, so you can use a different model for that. So in Ikigai, while we allow you to utilize all the other different models, and our AI Cast product automatically picks the best model, our use of graphical models in particular in AI Cast is able to, handle those use cases, a lot of those business use cases where the other models might fall short, but it also enables new use cases and new capabilities as well. For example, you're not always forecasting very stable products. In many businesses, you might be forecasting new products where you have no data at all. So for example, you're releasing a new type of shirt or you're releasing a limited edition, and you have no data or very limited data to go off and forecast. AI graphical models are really good at understanding the relationships, figuring out similar items, understanding those relationships, and actually allowing you to forecast, items you've never seen before, or conducting things like what if analysis. So if I run this new promotion, how would it change my demand? Or if I change the configuration of a particular product, how would it change my demand as well? And then finally, you can even run things like outcome-based simulations. So if I want to achieve a particular revenue or sales target, how do I, based on the relationships with data across all my different time series, how do I achieve that? And there's multiple use cases that this can unlock, such as now forecasting demand at any level of granularity, not just the highest level, because we can work with multivariate hierarchical time series, forecasting new products, looking at the effects of promos, and simulating how to achieve different business outcomes. So today, exactly, we see multiple customers across various industries using these capabilities in different ways, whether it's in retail, launching new products, whether it's in financial services such as insurance, looking at how much how do I allocate agents, how do I allocate parts across different hubs in manufacturing, what is the optimal inventory to produce during the holiday season. In many cases, how you deal with Christmas or Prime Day or other holidays is very different than how you deal with the rest of the year. And even when is the optimal time to restock orders, manufacture new products, and so on. Now, I'd like to dive into a particular case study of how one of our customers is using Ikigai and AI Cast. So we have a customer that's a highly seasonal retailer with 1,500 stores across the country, selling over 10,000 SKUs, unique SKUs. They use AI Cast for forecasting both individual store sales as well as individual SKU sales. And they have some interesting challenges. For example, their sales are highly seasonal, which means there's almost no year-round data. They introduce several new SKUs every season. So many SKUs have no history whatsoever. And their stores are pop-ups, so they move around every single year. So you either have to take data from related stores or kind of simulate how a new store might actually behave. And before Ikigai, they were primarily forecasting completely in Excel. Now, utilizing Ikigai's AI Cast enabled them to unlock several new functionality, which ultimately led to an 80% improvement in their forecast accuracy. So with our AI Cast and graphical models approach, one, they were able to discover relationships across SKUs, across different years. So for example, if we're going back to my red shirt, you might discover that blue shirts and brown jeans tend to behave very similarly to red shirts. So we can actually use data across those to boost the forecasts. Or maybe, this year's red shirt sales looks very similar to red shirt sales from 2019 because in 2020 and 2021, things were very out of whack, very different because of COVID. In 2022 and 2023, things were changing, but not back to normal. And then now data actually looks like pre-COVID. So we're also able to discover relationships across years. They're able to discover relationships across stores and across years as well, and model new products and stores that have never been seen before. So again, with our AI Cast model, we're able to use the graphical models behind the scenes to actually discover all of these relationships across SKUs and then pick the best model for all these each of these 10,000 stores and each of these 1,500 SKUs. And finally, with the platform, we're able to enable expert in the loop. So while AI is great at producing all of these thousands of forecasts, they might have some knowledge the experts or the forecasters might actually have knowledge which allows them to nudge the forecast closer to what they should be. And the AI is able to take this into account. So we're able to generate most of the forecast for thousands of products, thousands of stores, but then flag which ones might need adjustment for the expert to actually go in and fix. And then the AI model, our graphical models, learns from that as well. So I'd love to kind of now pass it on to Camille to actually see how some of that looks like in action. We've talked about a lot of different concepts and what's going on behind the scenes, but it's always great to see what all of this looks like in a product as well.
Awesome. Well, with that, I also want to say that we've got the Q&A functionality here as well. So any questions that have come up through Vinayak's portion or questions as I'm going through, please feel free to use the Q&A. And I'll use about 10 minutes here, and then we'll open up the floor to go through those Q&As and answer them. So hello, everyone. And Vinayak, thank you for the great start to this session. Really useful information and a few things, nuggets that I haven't picked up on before. As Alex introduced me, I'm Camil Blanchet. My background's in neuroscience and master's in AI from Northeastern. And then I've been working with the technology and sales team at Ikigai for over 3 years now, implementing the types of forecasting using our graphical models on our platform. So I'll take you through a few views today on our application for how we think about model selection. So first, I'll start with a little bit of a recap of what we showed last week, some of our underlying technology around graphical models, in particular, that time to vec concept that Vinayak mentioned. And then I'll take you into our builder view. So underneath the hood, the way that we implement our graphical models and other system capabilities that we've developed. So to start, we've got our reference application for demand forecasting. And we always think about what are the ultimate business outcomes that we're trying to drive with forecasting. And so in this case, we're using exception-based planning, where we're going to be prescriptive towards a demand planner for what their reorder points are. So connecting a forecast, the sparse data or the historical data that we've trained on in the forecast to the actionable insights that the demand planner is ultimately going to make decisions based on. So in this case, prescribing when different reorder points have come up based on our demand forecast and inventory levels. Another way we think about this is with promotions analysis or scenario analysis. So on the right-hand side here, you can see we're running an analysis of what the sales lift from a new 10% promotion would look like. So once we've modeled the underlying data, which is what we're seeing on the left here, which is our visualization of our time to vec technology, then we can start to play around with the levers in the underlying data and say, if we change the pricing or if we apply a certain type of marketing spend to or campaign, then what's the impact on sales going to be for your forward-looking projection? So time to vec powering scenario analysis. And then this is where I take you underneath the hood. So where do we implement our models? How do we connect to data? And how do we think about model evaluation in particular? So this is a flow view that we have. So we're pulling in two data pieces or two data sets, historical sales data, and then one external data stream, historical temperature data on a zip code level. We're plugging those into our forecasting model, AICast, that's our graphical model. And then that model is trained in producing a demand forecast. So I'll unpack our forecasting model. That's our most used model. And then I'll take you through some of the other graphical and other models that we offer on our platform and why we offer these different models. So if we double click on our forecasting model and we create a new model, so we'll create our example model here. We've got a few different parameters that are required. So the time identifier and the ultimate output, which is the value column. And we're going to start in the training mode. The core configuration that we look at for AI cast is the model selection. So on the right-hand side here, you can see that we've got 4 different models that we're running within this one AI cast facet. So we've got our additive, base, LGMT, and SMA models. And then we've always got an extensive suite of additional time series and forecasting models that we run. So based on what Vinayak was showing about large graphical models and the power that large graphical models have for forecasting with sparse and complex hierarchical data, why are we running 4 or 5 different models underneath the hood here? And the answer is pretty simple. It's that we need to compare and benchmark our models at all times. So every customer who comes into us, we're not just going to run a forecast. We need to run a forecast and then evaluate that forecast compared to what they currently have. So that gets back to the poll question at the beginning. If you're working from spreadsheets, you might be using a statistical model and a REMA model. So we want to run your REMA model side by side with our graphical model. If you're running a more advanced forecasting model, like a profit, let's say, then we'll also run that side by side. So ultimately, we're going to select the model that works best, but we need that benchmarking across these different models to make sure that we're choosing the best model. And that's typically our graphical model, but we're always going to do that side-by-side comparison. So that's our AI cast functionality, which focuses on large graphical model or on our graphical model and then comparing the outputs from our forecast compared to other models. We've also got a number of other machine learning models, which we can see up top here. So the first one is the AI cast model. That's the one that we just went through. That's our core forecasting model. We've got a number of different LLM capabilities. So in the data input and processing side, we'll use LLMs to take unstructured data and structured it, or perform something like sentiment analysis. AI Match is our graphical model for data stitching and reconciliation. There are 2 versions of that, the supervised and the unsupervised, just based on whether you're providing feedback to the model or not, based on what would be a match within 2 data sets or what wouldn't be a match. So that's our data prep model. And then I just showed you a view of this model, our AI plan supply chain model, which is our scenario analysis or optimization model. So when we run that 10% promotion, or when we simulate that 10% promotion for a particular product in our forecast, AI plan is what's running that scenario. We've got AI predict for classification. And then a full suite of different time series analysis in open source models. So extracting change points. So Vinayak mentioned in the case study earlier for that large retailer, detecting the change points around COVID in particular and isolating the impacts of COVID on their sales history. Anomaly detection is a very useful tool that we run through all of our time series data that we collect. And then we've got our open source models as well. So if we need to bring in a model that we don't currently have on our platform, an open source model or something that you're using that we want to benchmark against, then we can bring in these open source models onto our platform and use them natively within these flow views. So hopefully that gives you an idea of our forecasting methodology, the way that we'll run multiple models to make sure that we're choosing the best model and benchmarking against what you're currently using. We've also got a number of different white papers benchmarking our graphical models and a number of models, the most commonly used models we see on the market across different types of data sets. So sparse data sets, very extensive or complex data sets. So we can certainly touch more on that in the Q&A, which I'll hand it over to Alex now for that.
All right. Thanks, Camille, and thanks, Vinayak. Both of those topics were extremely interesting. It is now time for questions. So I've got a few queued up and ready to go that have been coming in. The first, Vinayak, I'll direct that to you. So, looking at, it's one thing to have a model that produces an output, it's another to be able to interpret it to the business. So the question is, how do different models balance accuracy with interpretability, and how do we balance that trade off at Ikigai?
Great question. So I would say first of all, the most interpretable models are probably the statistical models as well as graphical models, because what they do is they can kind of tell you effectively the correlations with other pieces of data. The statistical models with, where in past history is something, did something look like this and what is it using? And then the graphical models can tell you that in time, but also what we call in space. So for example, which skew also looked like this. And because that skew behaved a certain way, this is highly correlated. This is why we think this other skew is going to be forecasted this way. Now, I would say the neural networks and foundation models are a bit more out of the box, or sorry, a bit more black box. Foundation models, again, they're looking at patterns across large corpuses of data. So, it might be such that, your business data looks a lot like maybe for whatever reason it matches weather data, and it might tell you that's the closest match and that's why, but that doesn't necessarily give you a kind of personalized kind of interpretability as to your business. And the way we typically see this with customers, or way we implement it, is there's a few signals that are good for kind of explaining. So one is, how is this year's trend, or kind of this time period, how does it look compared to the last year or maybe the last 2 years? And how does it compare to kind of similar skews or maybe similar regions? And usually by, looking at those sorts of things, we can start to understand why the forecast is what it is. So for example, with a particular customer, we saw that the forecast was way higher than it was expected. And if you look at the last 2 years, they had a certain year-over-year growth rate. But then this year for that particular skew, the growth rate was much higher, and it actually looked a lot like the growth rate of some other skews in previous years. So we could kind of pinpoint that out and say that's why the model is, doing what it's doing. Now, if you as an expert have some information and you think, hey, I actually don't think it's going to behave this way for whatever reason, then you can use expert in the loop to correct it, and then we'll do that.
Got it. Awesome. I'm going to stop my screen sharing so I can take a look at the QA and some of the other things coming in. Um, there is a question about how Ikigai and why are we able to handle predictions where there's very little data. Could you go into that a little bit more? And, when we say very little data, what exactly is meant by that?
Yeah. So in some cases, very little data could mean literally zero sales, zero history. In other cases, it could mean, we have a couple weeks of history. So the way we do that is we're learning not just relationships across time, so not just looking at the historical patterns, which most of the others have to do, but we can also look at other attributes. So for example, if we know that, going back to the red shirt example, it's a new red shirt, it's never been sold before. Well, we generally know that it's a shirt, we know it's red, so we can compare it to other shirts that have been sold in the past, other red things that have been sold in the past. We know, for other shirts, what else it's similar to. So we can utilize all the other attribute data to actually look for similar items, and then not just attribute data, but look at the attribute data to look for other similar items to forecast. We can look at location data. So for example, the way red shirts behave in Chicago versus New York, or the way shirts behave in Chicago versus New York might be different. So we take that into account when projecting how this particular red shirt will behave in Chicago and New York as well. And then of course, as we get more data, it refines, but that's effectively what we do, is we can incorporate some of that extra hierarchical data, whether it's product data, attributes, or location attributes, or anything else. External data such as holidays, weather, to help with that forecast.
Okay, awesome. I've got one more question, and it's how do you validate that you've chosen the best model for the data set? How do we know that we're picking the best model?
Great question. So, a couple of things. One is, from a pure numerical standpoint, we typically encourage WMAPE as the evaluation metric. So that's called the weighted mean average percent error. So it basically means, for your particular forecast, on average, how far away is it from, what actually happened? And that's a great metric. And numbers don't necessarily tell the whole story, but some of these interpretability things that you can see, for example, how does it compare to last year in terms of trends? How does it compare to the year before in terms of trends? How does it compare to other SKUs? Give you a more qualitative view on how the forecast looks like as well. So that's how you combine the quantitative as well as qualitative.
Thank you. Um, those are all the questions we had come in. So I think we can wrap this up. Just some key takeaways. This will be included in the deck that we're going to send out after, as well as in the recording. And I would just say this is the second in a series of five. So feel free, if you haven't registered for all of them, to go back and do that next time. I think is November 13th. That's my birthday. So please join us for that. We'll be talking about elevating time series forecasts with external data and AI techniques. So that's something I know a lot of people have asked about. How can things in the outside world help me understand what's happening in my business? So please feel free to forward to your friends who might be interested. And I'll thank our speakers again, Vinayak and Camille. And thank you everyone else for coming. We'll also be including a link to some resources you can check out if you want to get a little bit more information. And with that, we'll be concluding today's presentation.
Awesome. Thanks, Alex.